In this unit, we're going to be talking a lot about inverses, so let's remember about inverses. First, let's talk about what we're taking the inverse of, and that's of a quadratic function, y equals x squared. So I'm going to make a table of values so that we can graph this. When x is negative 3, if I square that, I get 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So if we look, there's x and there's y. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and I'll go ahead and go all the way up to 9. I'm going to go ahead and plot these points. Negative 3 gives me 9, negative 2 gives me 4, negative 1, 1, and so forth. And remember, quadratic, you get a mirror image. Left side and the right side are symmetrical. And this is a function. Each x value is paired with exactly one y, one output. All right, now, let's remember how to find the inverse of something. We're literally going to switch x and y. So if we switch x and y, we end up with x equals y squared. Another way to look at that is look at the table. If you're switching your x's and y's, you're literally going to switch your x's and y's. So they would actually switch. And when we plot these, well, I'm going to need a lot more space. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is associated with a negative 3 for a y value. 4 is associated with a negative 2. 1 goes with negative 1. 0 goes with 0. 1 also goes with 1. 4 goes to 2. And 9 goes to positive 3. We end up with a quadratic relation. If you remember back from conics, this is a horizontal parabola, x equals y squared. It is not a function. So how could we change this inverse from being just an inverse relation to actually being a function? Well, let's look a little bit more in detail at the relation itself. Y squared equals x. If I try to get y by itself, I'll take the square root of both sides. Y equals, and I know it's the square root of x, but my teacher always tells me I have to put plus or minus. That's why we're getting positive or negative values for y. All right, and that is not a function. Well, in Algebra 2, we're dealing majority with functions. We want to make this a function. So what we do as mathematicians is we're going to restrict the domain of the originals to only be positive values, which means we're going to restrict the domain of our inverse, and restrict the range of our inverse to only be these positive values. What that does is mean we're only going to be looking at this piece. That would be a function. It would actually be the function y equals the square root of x. That makes it an inverse function. So we have this parent function of the square root family. This is the square root functions. And if we look at it by itself, we're going to take away the rest of the graph. When x is 0, y is 0. When x is 1, y is 1. When x is 2, 3, 4, we get 2. 5, 6, 7, 8, 9, we get 3, and so forth. We're only looking at that portion. This is the square root function. Now if we notice, the domain, all of my x values, are greater than or equal to 0. Now also, my range, we had to restrict that. Actually, we restricted the parent, the original, but our range got restricted. We only decided to take the positive values. So we're looking at the y values that are greater than or equal to 0. Now, I want you to think back, why is the domain restricted? Well, I hope you remember I can't take the square root of a negative number. I'll get something imaginary. So that's why we can't take the square root of a negative number. Now let's think about what can happen with the square root function. Well, we could have something on the outside multiplying it. We could subtract something on the inside, and we could add something to the outside area. And I want you to remember what each of these parts do. If we multiply by something, that gives us a vertical stretch. Now there's also the option that it could be something negative that we multiply by. And if you remember what happens to our graphs, if we multiply by a negative number, we get a reflection or a flip over the x-axis. And we'll do an example of that here in a second. X minus h. Remember, when you're with the x, it does the opposite of what you think. So if you add, you're going to move to the left. If you subtract, you're going to move to the right. So an h minus h would actually move us right h. So h is that horizontal shift. That's moving me left and right. Now when we add or subtract at the end, what that's literally going to do with our graph is move it up or down. So this is a vertical shift. Oops, I can't spell. That's all right. That's a vertical shift. So I want to look at some examples of ones we could work with. And on each of these, we're going to look at the domain and range. We're going to take the parent and look at a transformation of it. So the first one, parent is fx equals the square root of x. So, square root of x. If we think about that, that's 0, 0. We just made a table of it. The square root of 1 is 1. I'm going to go on to 4. The square root of 4 is 2. And the square root of 9 is 3. So here is my parent function. What do you think is going to happen when I multiply by 2? 2 times the square root of x. That 2 is going to give me a vertical stretch. Literally what I'm going to do is take each y value, each output, and multiply by 2. So the output here is 0. Y value is 0 times 2 is 0. The output here is 1. 1 times 2 is 2. The output here is 2. 2 times 2 is 4. The output here is 3. 3 times 2 gives me 6. So I took each of my y values and multiplied by 2. That stretched the graph. It made it taller. If it had been a fraction, it would have been shrunken down. Now let's look what happened to the domain and range. The domain and the range of f of x, of the original, the domain are our positive x values including 0, because I can't take the square root of a negative. The range was restricted, so we're only looking at the y values that are greater than or equal to 0. Now because we're just stretching our y values, nothing has really changed for our domain and range. The domain is still positive values and 0, and the range are the y values greater than or equal to 0. But what happens when we shift it? Square root of x minus 3. Well, I better graph the original. When x is 0, y is 0. When x is 1, y is 1. When x is 4, the square root of 4 is 2. When x is 9, the square root of 9 is 3. Here's my parent function. Now, I'm going to make some really good points there. Because when I'm translating, in other words, moving left and right or up and down, it's easiest to use points that are already there and then just move them. So square root of x minus 3 means I'm going to move right 3. I'm literally going to move each point right 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So think about what has happened. Let's compare the domain and range of each. The domain and range of the original one. The domain are all the x's greater than or equal to 0. The range was all the y's greater than or equal to 0. When I look at this transformation, when I translate, now my x values start here. So my domain, the x values have moved. They've shifted. They're now starting at 3. Now my y values, I didn't move up and down, so the range, the y values, are still starting at 0. But what happens when I combine a few of these? Negative square root of x plus 2. Let's just predict what's going to happen here. The negative, well, teacher told me that if there's a negative in front, that's going to flip it or reflect over x-axis. It's going to be a mirror image. Instead of going like that, it's going to be down, okay? X plus 2. Or it does the opposite, so it looks like it's going to be adding 2, but it's really going to go left 2. Predictions for h of x. H of x is the function square root of x minus 3. So minus 3 inside is going to go right 3. And the plus 4 on the outside, that moves me up or down. So plus 4 is going to go up 4. Let's look at each of these on the graph, starting with our parent f of x, and we're going to talk about the domain and range of each of them. So I'm going to start with that parent function, which was, let's see, 0, square root of 0 is 0, 1, square root of 1 is 1, 4, square root of 4 is 2, and 9 gives me a 3. There's that parent function. Again, the domain of the parent are the x's greater than or equal to 0. The range or y's greater than or equal to 0. That first transformation, g of x, I'm going to flip this, going this way, and move it left 2. So if I flip that, well, it's still in the same place. Left 2 puts me here. Flip this, left 2. Flip this, now it's at a negative 2, and then moving left 2. Flip this, it's at 3, so now it's at negative 3, and then left 2. So it didn't change the steepness of it. It's not stretched or anything. The negative flipped it, and then x plus 2 moved it left 2. So you'll notice that my x values start there now. The x values have to be bigger than or equal to negative 2. The range, we didn't go up, it didn't shift up or down. We just flipped. So now my y values are going down. So I want the y values that are less than or equal to 0. Let's look at this last one. Square root of x minus 3, and then a plus 4. So we said that moved right 3, up 4. So I'm going to take each point from the parent and go right 3, 1, 2, 3, up 4. Right 3, 1, 2, 3, up 4. 1, 2, 3. Whoops, I think I counted wrong. 1, 2, 3, 1, 2, 3, 4. There it goes. Right 3, 1, 2, 3, 1, 2, 3, 4. And then this one's going to be way out there. So I'm just going to go ahead and graph it. My x values now start there. So the x values have to be greater than or equal to 3. The y values start there at 4, and it goes up from there. So my range has to be the y values greater than or equal to 4. So you can almost tell, because those horizontal or vertical shifts, what your domain and range are going to be. We're going to make this prediction. So, square root of x plus 5. Well, that's a left 5. And the minus 1 is a down 1. But it's not flipped or anything. So the left 5 means we're going to start over here. So the x values are going to be greater than or equal to negative 5. Down 1 means I'm going to take that parent and move it down 1. So my y values have to be greater than or equal to negative 1. It's almost like you're taking all the x values that are greater than or equal to h, because remember that's an x minus h, plus k, and the y's would be greater than or equal to k. Now, part of the reason we're doing this activity is so that you can start to make predictions about what the changes to the parameters in the equation will actually do to the graph and to its domain and range without ever having to graph it.